In this example today, we will use ANOVA and regression to understand the prices of some used cars. So the data has been collected from a web page where people sell their cars for second hand, and then you see that most of the people are private people selling their cars, and then we have the price in dollars, and then whether there has been a test to to show that the car is in good conditions, the vehicle type, the year of registration of the car, the kind of gearbox, manual or automatic, and the power of the engine, then the model, the number of kilometers of the car, and month of registration, and fuel type, the brand, and whether there is a not repair damage, and the date that the announcement was created, number of pictures, postal code, and last time the car was visited on the web. So let's see if we can predict the price of these cars using all these variables. We see that we have about 50,000 cars, and after removing the not numbers, so those entries that are not complete, we have only 35,000. And yeah, as always, we remove data, for instance, when it was last crawled. Crawled means there are internet robots that go over all web pages, so we don't. This is not related to our model, so we will remove all those variables that are not related to the price, and then we will convert all these to categories. And then there is a little bit of handling here. So you see that there are dollar signs, there are commas, and there are kilometers. There are kilometers here, and again commas. So we want to convert all those to numbers. So we convert to numbers the price after removing the dollars and removing the commas, and the same for the number of kilometers. And then we have to make sure that they are floats. Okay, so yeah, this is our model. Now let's explore it. So for instance, as always, these are the averages, prices, year of registration, power of the engine, and number of kilometers. So you see that the maximum, there are a few things here that are interesting. First, the number of kilometers, the maximum is 150,000. So that means that these German people, they change the car when the car reaches 150,000 kilometers. So it seems that at least on this web page, it is not allowed to sell cars with more than these. And then the newest car is 2018. The oldest car is 1931, so this is probably an outlier. And also in terms of power and price, you see the maximum here, it is huge. This is kind of a rocket, and also the price here is also huge. It is $10 million. So yeah, let's get rid of most of these outliers, and for that we will use this thing that is you compute something called the set score, that is the variables normalized by the mean and standard deviation, and then anything that is who has a set score larger than 3, it is removed. And then we go down from 35,000 to 33,000, so 2,000 cars were outliers in terms either of price or year of registration, power of the engine, or so on. And now the range of values are much more understandable. So there are cars that have zero price, some others the maximum is 33,000. The average, the median is 3,600. The mean is a little bit larger, so that means that the price is skewed, as we see. When the mean and the median they don't coincide, is because the distribution is not symmetric, and this is the case now. And then the year of registrations, they are much more normal. So cars with almost 30 years old, the newest cars probably coming from last year. Then the power is something more reasonable. Okay, so let's explore the correlation matrix. This only applies to continuous variables, and we see that the price is correlated. We have here the column price. The price is very highly correlated to the year of registration, and the correlation is positive, meaning that the newer the car, the higher the price. The same for the power. So there is a strong correlation, and the higher the power, the higher the price. And the number of kilometers, it is the opposite. The higher the number of kilometers, the lower the price. That is why we have a negative sign here. And yeah, we can make this graphic representation of the correlation matrix. And then let us explore the relationship between the price and the categorical variables. All this has been done with numerical variables. So let's explore with the categorical. So is there any relationship between the price and having a test? And no, it doesn't seem to be such a relationship. So having a test to sell your car doesn't seem to affect the price. Then is there a relationship between price and vehicle type? And let us see. Yes, there is a relationship. The strength of the relationship is given by this F. This F is a kind of signal to noise ratio. The higher, the stronger the resolution, the relationship. And if we make a plot, we see that not all the means are the same. So we can see that, for instance, the most expensive ones are Cabrio, Coupe, SUV, and small cars. They are cheaper, and yeah, so they go in the expected direction. And is there a relationship between price and gearbox? And again, yes, there is a relationship. And we see that automatic cars are more expensive than manual cars. Is there a relationship between the month of registration and the price? And it seems that there is a relationship, but it is actually a very strange relationship. We have month of registration between January and December, but there is an extra category here, 0, that we don't understand what it is. And yeah, so it seems that it is some strange value that somehow it is affecting the price. And is there a relationship between price and fuel type? And we have different kind of fuels. So we have liquid gas, standard fuel, standard gas, diesel, hybrid, electrical cars, others, and again there is a there is a significant relationship. Not this one. This is almost elastic. So there is a relationship between those, although the relationship is not too strong. And again, here we have a graphical representation. We see that the most expensive cars are hybrid and diesel. And here is the relationship between the price and the brand. So we would expect a relationship here, and this is what we get. Although the relationship, you may remember the previous F, and they were in the order of 500, 3,000, some of them, and here it is a very weak relationship, but not all brands have the same price as expected. And yeah, so here we have the this is checking normality. We don't have the average prices per brand. Okay, so now price and not repair damage. So if you have a not repair damage and you are selling your car with a non-repair damage, does it affect the price of the car? And the answer is of course. If it has a non-repair damage, the price is much lower than if the car is in good conditions. Okay, so now we may look at what are the we can sort all these discrete variables by their importance. The most important variable is gearbox, and then not repair damage, and then for vehicle type, fuel type, the brand is relatively unimportant, month of registration is not that important, and the test that we already saw that is not significant. So when you construct a 2, 3, 4-way ANOVAs, you would like to use the most explanatory variables. So we will start with gearbox and not repair damage. Okay, so as we did in the previous practice, we will use this interaction plot. So if these two lines, if there is a shift between the two, that means that the not repair damage makes a difference. If the slope is not flat, that means that the gearbox makes a difference. And if the two slopes are different, that means that there is an interaction between the two. So yeah, we construct our model, and then we get that the gearbox is the most explanatory variable, not repair damage too. The interaction between the two is also significant. You see that all the p-values are 0 or very close to 0, but the f is not that important. So the two most important variables by far here are gearbox and not repair damage. There is an interaction between the two, but it is not a very strong interaction, although it is significant. Okay. And what about gearbox and vehicle type? So again, we see that there are differences by vehicle types, there are differences between gearbox, and not all the slopes are the same, so probably this is also significant. And again, we get the same result. So gearbox is extremely important, vehicle type not that much, and there is an interaction that is significant, but it is very, very weak, as we can see here. So not all the slopes are the same, but the slope doesn't change that dramatically. And let us explore now gearbox and fuel type, and we get the same kind of results. So gearbox very important, fuel type not so much, and the interaction, it is significant but very weak. And again, we have the same kind of representation here. Okay, so now let us construct, these were the two-way ANOVAs, only using two predictors. Now let us use all the predictors that we have learned. And we have seen that the interactions are relatively weak, so we can drop them. And actually, if you notice, we have been using here specifically ANOVA functions from some library, while here we are fitting a general model, a general linear model. So the result is the same in the sense that we can fit the ANOVA models with these two functions, but the report that we get from this fitting will be different from the ones we get in here. So here we get the ANOVA table. Now we will not get the ANOVA table, but we get the results as a regression. So here we have r squared. So we see that a model, an ANOVA model using 4 predictors is explaining about 26% of the variability, the model is extremely significant. So, and we can see that all the values are significant, maybe not the intercept, but gearbox and most of the vehicle types, some of them are not. For instance, the small cars, they don't have a significant effect on the model somehow because they serve as a baseline. And the same here, the normal gas cars, but then all the others, most of them, they have an effect, although not too strong probably. And yeah, so how strong or not strong the model is, you have it through the T. So the T here plays the role of the F. So the strongest variable is the gearbox, and then we have the not repair damage, and then this one, SUVs are also important, coupes and cabrios. So somehow these are the same information that we had before, and all the others, they are much weaker influences. Many of them are not significant. Okay, but so that would be enough for the ANOVA presentation. But as I told you, what we have now are tools to understand the world. So with this ANOVA tool, we have been able to explain 26% of the variability, and we want to understand the prices of these cars. So can we do better with the tools that we already have? And we can. So we will use regression, and for regression you may remember that it is better to work with centered variables. So we construct a model with a centered variable, and yeah, so we have here the different predictors that will be the continuous ones: the year, the power, and the number of kilometers. We see that this one is really explaining much more than what we were exploring before. So the year, the power, and the number of kilometers, they really explain more than the shift, year, and the other variables, not repair damage, so much more than those. And then we have here what is the intercept? The intercept is the average price, or somehow related to the average price, and then on top of that you get some values. So for instance, for every year your car is depreciated about $500, and every extra horsepower gives you an extra price of $50 per horsepower, and then every kilometer is subtracting from your value this amount. So all of these effects are significant, and the T values, you see that they are much bigger than the ones that we had before. So we have 300, 100, minus 71. We can compare to this. Minus 71 is already much bigger than the biggest value that we had before with the gearbox. Okay, so let us see now. Yeah, the R squared was here, so 65% of the variability, and now we may explore for interactions between year and power, year and number of kilometers, and power and number of kilometers, and we see that all of them are significant. Now we have gone up to 73% of the variability, and then we may construct a model in which we also include the discrete variables that are somehow related. And now when we include these discrete variables, what we see is that we go from 73% of the variability to 76% of the variability. So adding the discrete variables, once you have accounted for all these ones, they are not so important. So the manual shift, the gearbox, the not repair damage. The not repair damage can make an impact, so we can look for the not repair damage, gearbox. So they make an impact, but still the most important variables are the year, the power, the number of kilometers, the interaction between year and power. So the interaction between year and number of kilometers and number of kilometers of power and number of kilometers. So for instance, some of them we easily understand. So if you have a new car but it has many kilometers, then the price drops. That is why we have this negative sign. And you may equally try to explain the rest. And here, for instance, we see that the fuel type doesn't matter, and the vehicle type almost doesn't matter. You see, all of them are very small except for the SUV. Yeah, so now we have a good understanding of what is the price, what makes the price of a second-hand car. So this would be all for today, and see you next time.